Hi everyone, this is Mr. Tam. Today we're going to actually start our first lessons, and we'll be talking about something called linear function in chapter 3. Yes, we're not actually going to talk about differential equation until we get to our second chapter, which is chapter 10, because we need to understand some basic before we can actually talk about differential equation. We need to understand how to represent the solution to the differential equation first, and that's actually linear algebra. So today we're going to start with would be something called linear functions. So you might think that, oh wait, I know what linear function is. I learned that back in like 8th grade. That's a function whose graph is a line. Well, that is actually not true. In linear algebra, we define linear function in a little differently. So I want to show you, and you're going to need to remember some of this stuff from last year, chapter 2, in order to do this. So in case you didn't, chapter 2, we learned a little bit about matrix. And how do we use matrix to solve system of equation, which is actually surprisingly what we're going to talk about in chapter 3 a little bit. So let's start with the following. So the first thing I want to talk to you about is something called matrix representation. So to start off, let's imagine you're given a system of linear equation. Let's say you're given a system of linear equation to begin with. And you will learn from last year, we can always represent this system in what we call matrix form. So for example, suppose I have this two equation right here, 2x plus 3y equal to 5, and 4x minus y equal to equal to 3. And we're not talking about how to solve this system, but simply just learn how to represent this system. So one way to represent this is to actually rewrite it into this form, which is called a matrix form. So if you recall from last year, this right here is called a matrix A, which is called the coefficient matrix. This right here is our vector x, which is basically called the variable vector. And then this last one right here doesn't really have a name. It's usually referred to as vector b, which is usually called the right side vector. And it's kind of weird when you call it a right side vector if you write the equation backward. So we usually try to write it this way. So therefore, this expression right here just basically turned into something like this. Oops. Matrix A times vector B, vector x equal to b. And so we talk about, you have learned how to solve this system last year using some kind of matrix method, reduced matrix and things like that. And you probably also remember learning that system of linear equation like this one could have no solution, could have one unique solution, could have infinite solution. However, an interesting thing about it is the following. So if we look at this as a system, then it's fine. But what if we have somewhat a similar problem where we have the same coefficient matrix, but we have different b? Well, we will perceive it as a completely different system, but yet it's somehow relating to this one because it has the same exact coefficient matrix. And some of you might remember learning a theorems last year that I test you on. Let's talk about a concept like this. And don't worry if you don't remember, you don't have to go back and look it up. We will actually talk about it later on in this chapter. And because it's going to form the basis of how we're going to do any differential equation solution. So that means the theorem that you probably don't remember, or if you remember, it's great, would actually form the basis of chapter 10, 11, 12, 13, and 14, all of them. So you don't have to worry about it. We will definitely talk about it. You'll see it a lot. Okay? So the question is, if we have a similar system with a different vector B, but have the same vector A, is there some way to actually link them together? And yes, there is. And the way to do that is to actually reinterpret this system, not as a system of equation, but rather think of it the following way. Think of it as, what if we can interpret this more like you have a function that has an input that is x, which are the variables, and that have a specific output for the function. And so if I now have a different system where the vector b is different, then we basically just have the same exact function, but just have a different output that we try to solve for. So that gives us a little more flexibility, and not to mention that they allow us to actually use a function notation to kind of deal with a system of a linear equation, which then it condenses some of the things that we have to write. Remember, mathematicians hate to write. And also another thing is to give us more flexibility, because now we can use concept from function to help us deal with this. So the way to actually do that is actually pretty simple, is to learn to define a function that kind of fit this system correctly. So how? Well, in this case, if you look, this system of equation have two variables right here, x and y, and its outcome is also two variables, 5 and 3. So therefore, we can actually define a function that is from R2 to R2 that will allow me to actually represent what this function is supposed to do. Okay, so let's try this. So suppose I'm going to define a function, let f be a function where f map from R2 to R2. So therefore, meaning that this function has two independent variables that we plug in, and they pop out two dependent variables when we define the function. And so this function is a multi-variable function, vector value. And so let's define what this function is supposed to do. I'm going to define function f of xy to be equal to 2, 3, 4, negative 1 multiplied by xy. And so this function is basically what we call vector a of x, where a is our coefficient matrix 2, 3, 4, negative 1. And vector x is our variable vector, which is xy. And so then we can now rewrite our system the following way. Then our system simply become this equation. A system of two equation, two variable, simply turn into this. Simply turn into become, instead of a system, now we have an equation. So turn to the equation f of vector x equal to 5, 3. So notation-wise become a simpler way to write this equation. And also because now we talk about function, it might help us by using some of the function concept that we know. Now, this function is special. And the reason it's special is because, number one, it actually represents a linear system of linear equation. And because of that, it's actually referred to, in linear algebra, a linear function. Now, but of course, a linear function does not mean it's a line, because as you can see, this function is actually a function in R2, mapped to R2. Okay, so if you think about learn from last year, this function actually represents what we call a parameterized surface. It actually transforms a two-dimensional surface in R2 into another two-dimensional surface in R2. Okay, and as a matter of fact, if you really want to know, this function most likely if you have a rectangle or rectangular regions in R2 as a domain, its output will probably form some kind of parallelogram type thing in the range. But if you don't know it or you didn't see it, and because you didn't remember some of the things we learned last year, it's perfectly fine. Don't worry too much about it. But simply understand that this is not a line. It actually draws some kind of two-dimensional shape and then change into another two-dimensional shape. And it's definitely not a line. So then what is a linear function? Why do we use the word linear, but it's not a line? Well, because in linear algebra, the term linear doesn't actually mean linear like a line, but rather it actually represents like first degree. Function that form without any multiplication between the element being used. So, let's give you a proper definition of linear function first, and then we can talk more about linear function. So what is a linear function? So in linear algebra, we define a linear function as follow. So how do you define a linear function? So here's the definition. Let's say given a function f that map from Rn to Rm. So this function doesn't have to be, I guess, actually maybe I should rewrite this. Rn to Rm. So the domain and the range doesn't have to match, but they do have to be both like real numbers. Let's say the function map from Rn to Rm, and here's how we define a linear function. So let's say given two vectors in Rn, in the domain of the function. Let's call these two vectors x1 and x2. And let's say given two scalar, let's call them a1 and a2. Then in this case, the function f is linear if it satisfies the following condition. It is linear if f satisfy the condition. If I do f of a1 vector x1 plus a2 vector x2, the outcome of this would equal to a times a1 times f of x1 plus a2 times f of x2. Now it might seem like it's a simple property, but it's actually very important to make sure you understand what does it mean. Okay? So what does it mean? So remember we talked about last year, we talked about whenever we have properties of operation, one of the important part about properties of operation is that they would try to tell us that you can do things in different order and you get the same result. Which is important because remember, math, one of the key things about math is order of operation. You have to understand when you have to do a whole bunch of things together, which one to do first, based on the way it's written and based on an established rule of order. And if you kind of mess up which way or which order to do things, you're going to mess up the problem and you'll get the wrong answer. So a lot of the properties that we learn, it basically tells us that, oh, you can do it this way or this way and it will be fine because it's the same. So that's important. And here it is the same thing. A linear function has a very important property, is that you can either do a linear combination of the input and then put it through a function. So this is called linear combination of vector x1 and x2. If you take a linear combination of the input and you plug it through a function, It's actually the same, the equal sign, the same as you do a linear combination of the output of the function. So the important part here is that you can either do the linear combination before you plug into function f, or you can do a linear combination after you plug into function f. And a linear function will tell you that either ways you do it, you get the same result. Our dual functions satisfy this property. Answer is no. That's the reason why this type of function are special. Now, I'll give you an example. Show you some very simple example of what is a linear function and what is not. And you found that linear function have a very basic characteristic. So I'll show you this very simple example to illustrate. Okay. Consider a function right here. Consider function f of x equal to mx. So if you recall learning it from Algebra 1, mx is a linear function. It's missing a plus b part, so therefore meaning that this is a linear function. This is a line that goes through the origin with a slope of m. So consider a function. I'm going to ask you to do the following. Show that f is linear. Now, very important, this is a very important example because you will be asked to show a function is linear on your next test. So make sure you understand what's the expectation, what do I want you to show, okay? So how do you do that? So we'll have the function f of x equal to mx. So all I have to do is start the process to first define two elements within the domain of f. So in this case, our function is assumed to go from R to R. Because the variable x is interpreted to be a real number, represent real numbers, and then the output is just a real number times some constant m. So therefore will be a real number. And I'm going to say, let's say we have these two numbers, x1 and x2, and they're both in the real numbers. Okay. So this little symbol right here is like the letter E, basically represent that mean is exists within. So x1, x2 exist within the real numbers. So now what I'm trying to do is try to show that this property is true. So how? Well, you probably remember learning it last year. To show a statement, an identity statement like this, what you need to do is to show that no matter what a1, x1, a2, x2 are, the left side and the right side always represent the same thing. So I'm going to go ahead and do that. So let's see. So I'm going to go ahead and start with this. So suppose I take f of a1, x1 plus a2, x2. So in here, x1 and x2 are considered to be the input of the function, and a1, a2 are just two scalars. What's this equal to? Well, the function would actually take m and multiply by whatever input we have, a1, x1 plus a2, x2. So now it's a matter of trying to figure out what would this look like, and would that look like what's on the other side if I were to do it. So let's find out. So first note that they have a multiplication of m into a sum of two things, so distributive property apply. So therefore become ma1 x1 plus ma2 x2. Get so far? And now here comes the important part. Remember, to prove what we try to prove, we have to use property that already been established. So since we are here dealing with just real numbers, I can use what we know about real numbers and the operation involved to help me prove this. So there are two basic operations involved. One is addition, and the other is multiplication. Look at the first term right here. There are basically three things being multiplied together, m times a1 times x1. And based on associative property, as well as commutative property, I know that m times a1 x1 is technically the same as a1 times m times x1. Because of commutative property, I can reverse the order of m times a1 to a1 times m. And I can also do the same thing with the second part by saying it's the same as a2 m x2. And then I can say, well, associative property tell me that I don't have to multiply from left to right, but I can actually group them differently. So what I'm going to do is I'm going to group the mx1 together and multiply first, and mx2 together and multiply first. And now come the interesting part. So if I look at this right here, then that would tell me that would be a1 multiplied by m times x1, which is technically the same thing as f of x1, times a2 multiplied by m of f times x2, which is technically the same thing as f of x2. So therefore tell me that f of a1 x1 plus a2 x2 actually generate the same exact thing as a1 f of x1 plus a2 f of x2. So in this case right here with the function f of x equal to mx, it really doesn't matter if I combine things together first or do them separate. They will basically give me the same exact result. All right. Now, it might seem kind of abstract, but it's basically just doing something like this. Let me see if I can show you a different example. Okay. So let me show you an example, just basically what all this mean, because it's kind of hard to understand when you're just looking at all this a1, x1 and things like that. But to be fair, it's not going to get it. It's not like really that much better with the example, but maybe a little bit better. So imagine the following. So basically what this proof is the following. Let's say we go let f of x equal to, let's say, 3x. So in this case, m is 3. So consider the following. Let's say I want to evaluate this. Sorry. Let's say I want to evaluate f of 3u plus 2v. So how would I go about doing this? Well, I mean, the easiest way to do is the following. So one way, option 1, is that we just basically do what the problem tells me to do, which is what you probably remember learning back in Algebra 2 when you learned about composite function. You basically just plug this into function f to see what happened. So that means it's 3 times 3u plus 2v. So that would just come out to be 9u plus 6v. So that's option 1. And for most functions, that is the only option. You just basically do what the function asks you to do, and by plugging in the expression 3u plus 2v, and that's it. There's no other choice. But we now have an option 2. And option 2 is only available because of the fact that we have a linear function. What's option 2? Option 2 is instead of doing this linear combination for inside and then multiply, how about do the following? We rewrite this into this form. 3f of u plus 2f of v. So instead of having a linear combination of u and v, plug it through the function, we actually form the same exact linear combination, but just with the output of the function, f of u and f of v instead. And because the function f in this case is linear, the output will be the same. So let's see if that's the case. So that would be 3 times f of function u, function f of u would be just 3 times u, plus 2 times f of v, which is just 3 times v. So therefore, it would be 3 times 3 times u, that would be 9u, 2 times 3 times v, which is 6v. Voila! These two are the same. So that's what linear function give us, the option of either doing the linear combination, then plug into the function, or in some cases, plug into the function and then form the linear function, form the linear combination. And either way would give us the same result as long as the function f is linear. So to finish today's video, what I'm going to do is, how about we do an example of something that's not a linear function. And then I do want to talk to you about a very simple theorem. Or actually, maybe we'll talk about the theorem tomorrow. But we'll give you another example. So what happened to this function then? is the function f of x equal mx plus b linear? And you might be thinking like, of course it is. That's what we learned back in 8th grade. Well, I have bad news for you. Your 8th grade teacher been lying to you. Function f of x equal mx plus b is actually not linear, defined as a linear in linear algebra. It's actually not linear. Show you why. So consider the following. Consider that we have x1 and x2 within the set of real numbers. Okay? And we're going to do the same thing as what we did before. I'm going to go and try to do f of a1 x1 plus a2 x2 and try to show that this would equal to a1 f of x1 plus a2 f of x2, or show that they're not equal and therefore tell me it's not linear. So let's go and do this. So therefore that would mean that it would be, that would mean that this is m multiplied by a1 x1 plus a2 x2 plus b. So distributing the m would tell me that this is m a1 x1 plus m a2 x2 plus b. Now what I'm going to do is I'm going to try to do the other side of the properties. a1 f of x1 plus a2 f of x2, and see what happens. So that would be a1 times mx1 plus b plus a2 times mx2 plus b. And if I multiply this out, that comes out to be a1 m1 x1. Oh, I'm sorry. The m doesn't have a subscript. A1 m, a1 m x1 plus a1b plus a2m x2 plus a2b. And as you can see, these two expressions are not the same. Oh, actually, let me rephrase. These two expressions are not the same unless something must be true. Take a minute to guess. You can pause the video and try to think about it. And when you're ready, you can then unpause the video. These two expressions are not the same unless b is 0. And if b is 0, then this function is just nothing more than mx, which we already proven to be linear right here. Okay, so this function y f of x equal to mx plus b is actually non-linear. Oh, sorry. I should just write this. Is not linear if b does not equal to 0. And it is linear if b is 0 in this case. Good. Alright, it's almost 30 minutes, so I think I'll probably stop here instead of getting to the next thing I want to show you. So we'll stop right here for today, and then we'll continue some more tomorrow. Okay? Talk to you later. Bye-bye.